Hello and welcome to our lesson on logarithmic functions. So a log function is a function in which we're taking the log of x as our argument. So we're looking at the form y equals the log base b of x. So the log function again is where we're taking the log of some argument that is going to be unknown, and the x and the y in there make this a function. Now I know we technically have a third variable in there, b, the base. The base can be almost any number like with our exponential, except it can't be negative, and it can't be 0, and it can't be 1, and these should make sense as the base of the log, because if, let's say we had the log base, I don't know, let's go -4 of something, okay? That means we would be looking for of it to be equal to something, right? We would be looking for -4 to some power to be a positive argument. We can't take a negative number and raise it to a power and get it to be equal to an argument, okay? So our base can't be negative, and the same thing happens with 0 or 1. I can't raise 0 to a power and make it equal to any number. I can't raise 1 to a power and make it equal to any number. So those restrictions keep our base from being negative or 0 or 1. So I know we have technology that graphs for us, but in order for us to better understand what's happening with the log function, we're going to graph the old-fashioned way. So remember, any function can be graphed by just making a table the old-fashioned way. So that's what we're going to do here. So let's look at y equals the log base 2 of x. It's a little hard to look at it, in my opinion, to look at it in this form. If I was going to graph a log function, I would actually rewrite it in exponential form, because it's a little more concrete for me and easier for me to understand, and I think that's probably true for most people. So in exponential form, this would be a base of 2 raised to the y power equal to x. Now an exponential function we technically already graphed. So we graphed something that looked like this, but we graphed y equals 2 to the x power, where x was our independent variable. We plugged in and we figured out what y was equal to. However, in this case, it would be much easier to pick some values for y, plug those in, and figure out what's happening for x. So I'm going to put -2 in for y, -1 in, 0, 1, and 2, and what's going to happen is the same thing that happened in our exponential, except everything's going to be switched. So I'm going to put -2 in for y, then 2 to the -2nd is 1 over 2 to the +2nd, which would be 1/4. And then when I put -1 in, then I get 2 to the -1 is 1 over 2 to the +1, which would just be a half. Anything to the power of 0 is 1. Anything to the first is itself, and then 2 squared is going to make 4. So what's happening here is very similar to what happens with the exponential, but because we switched the x and y's, what happens on the graph? So at x equals 1/4, our y value is -2, so we're going to be like around here. And at x equals 1/2, our y value is -1. And at x equals 1, our y value is 0. And at x equals 2, our y value is 1. At x equals 4, our y value is 2. And then if we were to continue, if we put in an x value of 8, right? Or if we put in a y value of 3, we would get an x value of 8. So at 8, 3, we would have a point. And it's really the same shape that we see occurring with our exponential, but it's a reflection of that shape. So just so you can kind of see the two. Remember, the exponential would be crossing here at 1, and then 2 to the first would be 2, and 2 cubed would be 8. And so the exponential looks like this, where this is a reflection of that graph, where what happens here is our fractions are going to get smaller and smaller and smaller, and in this direction our graph is going to grow. So it's a reflection over the parent linear function y equals x. Okay, so it's a reflection where we have similar properties, just sort of opposite things happening with x's and y's. Okay, so this one's going to have, instead of a horizontal asymptote at y equals 0, it's going to have a vertical asymptote at x equals 0, and it's going to grow in this direction. So this was our log base 2 of x. Okay, so let's look at the next one here, base 3. Hopefully we know what's going to happen with this. Again, in exponential form, this would be 3 to the y power equal to x. I gotta sneeze. False alarm. Oh my gosh, sorry. I feel a sneeze coming. Okay, so I'm going to put in -2, -1, 0, 1, and 2 for my y values. So 3 to the -2nd would make 1/9 for x. This would make 1/3 for x. 3 to the 0 power is going to be 1. 3 to the first is 3, and 3 squared is going to make 9. So if we flip all these on the graph, then at 1/9, we're going to be at -2. So this part of the graph is going to look negligible. 1/3 we're at -1, and then here is going to be the exact same place where we hit the x-axis. And then 3, 1, 1 we have a point, and then at 9 and 2 we have a point. So this side of the graph is going to really look basically the same. What's going to happen is it's going to be on our exponential, it would be steeper, but it actually looks flatter on this one. So this is the log base 3 of x. And we probably know what's going to happen here if we have 1/2 to the y power equal to x. So let's put in -2, -1, 0, 1, and 2. We're going to see a reflection of a reflection, okay? If we put -2 in, 1/2 to the -2nd would be 2 over 1 to the +2nd. I should keep these in parentheses, which is just going to be 4. And then if we put a -1 here, this would be a 1 here, this would be a 2 here. Anything to the power of 0 is 1. Anything to the power of 1 is itself. And then 1/2 squared is going to be 1/4. So on the graph, again, we're going to see a reflection of what we did in blue. So at 4, x equals 4, our graph is down at -2. At x equals 2, we're at -1. And x equals 1, we're at 0. And then 1/2, we're at 1. And then 1/4, we're at 2. And so again, what we see is a reflection of the one that we had in blue, which is the same thing that happened with the exponential. Remember when we looked at 2 to the x versus 1/2 to the x power? Okay, we saw reflections of the graph. So this was the log with a base of 1/2 of x. And actually these are, I don't know why I didn't put the equals y. Let's put equal y there. These are functions. And there it is, okay? So very similar things happening with these graphs that happen with the exponentials, which makes sense because we could rewrite these in an equivalent exponential form, but not exactly the same. Almost the reverse of what happened with our exponentials, where, remember the exponential function? So the exponential function looked like this, where they all had an infinite domain, and they all crossed the y-axis at 1 and didn't touch the x-axis, where one was increasing, one was decreasing, but all those properties were the same. It's the reverse here. So for these graphs, we have a restricted domain, okay? Look at the domain. We have a vertical asymptote at 0, so no graph is happening over here. So our domain is going to be approaching 0 and going forever toward positive infinity, and our range is unrestricted, which makes sense in the exponential form, right? I could plug anything I want in for the x's. It's just going to, for the y's, it's just going to restrict what can happen for the x. Then in these cases, we don't have a y-intercept. There will not be a y-intercept. But they all cross the x-axis at 1, 0. Again, that was the reverse of what happened with the exponential. And the exponentials had the horizontal asymptote at y equals 0. These ones have vertical asymptote at x equals 0, which is our y-axis this time. Okay, and in just like with the exponentials, when our base is bigger than 1, what we see is exponential growth. And when our base is some fraction between 0 and 1, what we're going to see is, what did I say, exponential growth? Yeah, when it was exponential, we had exponential growth when our base is bigger than 1, and then exponential decay. Here, it's log growth when the base of the log is bigger than 1, and it's log decay when the base of the log is some fraction between 0 and 1. So here we had a base bigger than 1, graphs that were increasing, creating what we call logarithmic growth. And when the base is some fraction between 0 and 1, then the graph's decreasing and referred to as exponential or in this case, logarithmic decay. Okay, so almost the reverse of what we saw with our exponentials. Now, this is a typical function. The transformation rules apply just like they do with all other functions, parent functions. So our standard form is going to have a times the log base b of not just x, but x minus h. And then after our function, we can add some value for k, where a does the same thing it does with every other parent function. It tells us whether or not our graph is going to reflect over the x-axis. It also could stretch or compress the graph, so it affects the width. And h would represent a horizontal shift in the graph. Does it go left? Does it go right? And then k represents a vertical shift in the graph. So is our graph going to, oops, I wrote h. Is our graph going to shift up or shift down with some value for k? Okay, so log functions. Let's see then if we can identify some transformations. So if we're comparing to log base 2 of x, this minus 3 is going to shift our graph to the right 3 units. And then this plus 1 is going to make our graph shift up 1 unit. Here, if we put a negative, it's going to reflect our graph over the x-axis. Reflects over the x-axis. And then the 3 is going to be a vertical stretch of our graph. So vertical stretch by a factor of 3. And then here, the 1/2 would be a vertical compression of the graph by a factor of 1/2. That's a compression. And then this negative inside here is another reflection, but this time it would reflect over the y-axis. So all the same transformations that we've seen in the past, they still apply here. So then if we were looking again at y equals log base 2 of x as our parent, if we wanted to shift it left 2, down 3, reflect it over the x-axis, and vertically stretch it by a factor of 4, what would the transformed function look like? So if we're going to reflect over the x-axis, then we're going to start with, let me color code here. If we're going to reflect over the x-axis, then we're going to start with a negative. If we want to vertically stretch by a factor of 4, then we're going to put a 4 out here. And then our parent is going to be the log base b of something here. Normally just an x, but this time we're going to go, it says left 2, so I want a plus 2 in here. And we're also going to shift, I'm running out of colors, we're also going to shift down 3, so I need a minus 3. And if you put that function, oh, I don't want a base of b. This tells me right here, base of 2. So let's put a base of 2 in there. If we graphed y equals log base 2 of x, and we also graphed y equals negative 4 log base 2 of x plus 2 minus 3, we are going to see all of those transformations occur. So Desmos could be used to verify that work, okay? Now, what I want to show you is a connection, again, between logs and exponentials, which I showed you a little in the beginning, but just to get it all concrete here. If we were to, let's look at the exponential first. That's the one we have in red here. Okay, when we plugged in our values for x, we saw what happened for y, where we had our infinite domain. Okay, we had our range that started at, or approached 0 and went up forever. We had our y-intercept at 0, 1. We had no x-intercept, and then we had a horizontal asymptote at y equals 0. Y equals 0, which was our x-axis, thinking. Okay, so that's what happened with our exponential. Okay, what we just saw was if we had the log base 4 of x, that all of that would be reversed. Okay, all of that would be reversed. We would switch the domain and the range, so for our blue one here, our domain is approaching 0 and going forever to the right, where our range was unrestricted. This graph went up and down forever. Where we did not cross the y-axis, but we crossed the x-axis at 1, 0, and we didn't have a horizontal asymptote at y equals 0, we had a vertical asymptote at x equals 0, which was our y-axis, where all of these properties were switched. So we see these two were reversed. Okay, we see these two features reversed, and maybe picky and choosy about my errors, and we see these basically flip-flopped as well. And that is because these functions are, do you remember what happens when we have a reflection over this, or when we switch the x's and y's, or switch all of the properties of the x's and y's? We have a name for that relationship. These functions are inverses. They are inverses of one another. Okay, so it's a little tricky because when I first introduced you to logs, we took an exponential and wrote it in an equivalent log form, and now what I'm telling you is that exponentials and logs are inverses. Okay, still true. So let me show you how this all connects. So technically, if we had y equals b to the x power, right? There's where we started all this with an exponential like y equals b to the x power. We said we could rewrite that in an equivalent log form. So the equivalent log form would be the log base b of y equal to x. Or actually, let me put this in reverse here. So it would be x equals, remember the exponent is the answer. It'd be the log base b of y. Now when we want to find the inverse of that, when we want to find the inverse of a function, remember what we end up doing is we switch the x and the y. If we switch the x and the y, then we end up with y equals the log base b of x. Those two functions are inverses. So here, these functions are equivalent. We can take an exponential and write it in an equivalent log form. But then these two functions, these are inverses. So y equals b to the x power. It's equivalent to x equals log base b of y, and the inverse of y equals the log base b of x. But notice what's happening from the exponential to the inverse function is that the y's are in the same spot, right? And the base of b is in the same spot, right? And then lastly follows the x, okay? Any exponential and inverse with the same base are going to be inverses. So for any exponential function, b to the x, the inverse, remember our inverse notation, is the log base b of x, okay? So any exponential and log with the same base are going to be inverse functions. So if we had 5 to the x, the inverse is going to be log base 5 of x. If we had 7 to the x, the inverse is going to be log base 7 of x. Okay, so we can take our exponentials, put them in equivalent log forms, and then switch the x and the y to make them inverse functions. Okay, and we're going to talk more about inverse functions in our last topic, but I think you've got enough to get you going on the log function practice. But as always, if you need some extra help, then just reach out. All right, guys.